Thank you. So my name is Ani, as I said. I'm a graduate from UC Berkeley. I did my undergrad there. Twitter is my first job out of college. And one of the main things that I've worked on Twitter so far is a technology called Tsar. Tsar stands for the words TimeSeries Aggregator. So let's just dive into it, and I'll try and leave time for questions at the end. So at the very outset, what is Tsar? So SAR is a framework and a service infrastructure that allows one to perform time series aggregation. So what does the word time series aggregation mean? If people in the room are familiar with something, have used Google Analytics, if you have your own website and you embed some Google Analytics code in there, Google Analytics will provide you with a dashboard that shows you how many people have visited your website day over day. And it gives you a time series of visits to your website. It can break this down by various segmentation, like the location of the different users, the gender of the different users. So it gives you some metric over which you are aggregating, and then it produces something that you care about. So in your case, it might be visits to your websites, and then it's producing a count in this case. So in the case of Twitter, time series aggregation is a pretty common problem. We anticipate that it probably solves about 60–70% of the various analytics needs that we have. And previously, we had various engineers within the company who would build their own analytics frameworks that performed and repeated the same problem. And so we abstracted away all of this into one common framework that has a lot of optimizations built in and that allows it to scale to the kind of events, the scale that Twitter needs, essentially. So, as we said, time series aggregation at Twitter is a pretty common problem. Some of the places where we would use it are various data products. So I'm an advertiser, I'm BuzzFeed or I'm Nike, and I'm advertising on Twitter. I want to see how my promoted tweet campaign is performing. How many people are clicking on my promoted tweet over day 1 versus day 2 versus day 3? How many people are favoriting my promoted tweet? How many people are following me? So we're surfacing some metrics in a time series to advertisers. It's very useful internally for different business metrics. For example, if I'm working on the platform relations team at Twitter, I want to know which client applications are using Twitter's API the most. Is there a particular API endpoint that is most common, that is the number of calls to this API is going up over time? Is there a particular client app that is getting a huge number of tokens being granted because there's a huge amount of adoption? Is someone not using our API in the best way? So there's a lot of internal business metrics that are useful for us to track, and those also fall into the class of time series aggregations. And then it's also useful for engineers themselves. They manage various services, so they want to track their service health over time. What is my success rate over time? How many requests is my service getting over time? How many failures does it have over time? And so on and so forth. So there can be many classes, like externally facing, internal business metrics, internal use, that all fall into the category of time series aggregation. So the parts that make it hard to do, as always, is scaling such a system. Twitter processes tens of billions of events per day. It inherently is a real-time platform, so you need to perform real-time computation. And you need this to be a robust system. You can't really have your time series aggregation job go down and then tell your advertiser, hey, we don't have metrics for these 15 minutes because our aggregation service went down because it got too many events and it couldn't scale to your needs. So how do you make it robust while giving real-time metrics? So time series aggregation, solving this problem wasn't solved over time. It wasn't solved just by me when I joined Twitter. It's been a multi-year effort over many, many years. Many people in this room, I'm sure, are familiar with MapReduce. At Twitter, we built out a library called Scalding that provides an abstraction. It's written in Scala. It's available on GitHub. It provides an abstraction over MapReduce and allows one to specify MapReduce jobs easily. We had acquired a company called Backtype that had a technology called Storm that provided real-time computation. And we've been working, and so so Storm would provide real-time computation. Scalding would perform offline computation. We then developed a library called Hummingbird that is also open source and is available on GitHub that combines Scalding and Storm, that provide where you can plug in any online platform and an offline platform, and it gracefully allows you to write one Hummingbird job that gets translated into an offline job as well as an online job. And we'll discuss what the use cases of this are. So the Hummingbird library is kind of at the very core of the SAR framework, but it's a library. And what SAR provides a framework. It provides a service infrastructure on top of Hummingbird. It provides the tooling in an easy manner so you can write an offline job to read in raw logs, specify dimensions that you want to aggregate on, compute the metrics that you care about, store it in a data store in an efficient data model, provides a query service by which you can query the data. It makes it easy so that you can aggregate data on a minutely granularity or an hourly granularity or a daily granularity. It makes it easy to perform restatement tasks like backfills. So there's a lot of service infrastructure that is provided by the Tsar framework as it builds and expands on top of the Hummingbird library. So it's been a multi-year effort over the course of many years, as I said, to develop the Tsar framework. And the whole goal is that it abstracts away all of the data pipeline logic from the user and allows the user to only focus on their business logic. So a typical aggregation job, like what does it look like? Somewhere you have raw event logs that exist on typically, in the case of Twitter, on HDFS. What do you mean by an event log? An event log is, say I go and I favorite Sally's tweet. That would send an event back to Twitter saying that user Ani went and favorited Sally's tweet at a particular timestamp. In what data center did that event take place? Like what client application ID did I use? What OS did I use? And so on and so forth. So there's one log event that encapsulates a large number of fields, like maybe about hundreds and hundreds of fields, hundreds of bits of information about that event. This gets sent back to Twitter's data center, and then using the scribe pipeline, these events get logged onto HDFS. Your aggregation job typically only cares about a few of these fields. Like if I want to just aggregate a number of favorites from each tweet, then all I care about from this log event is what was the tweet ID on which the favorite action occurred. That's the only event that I actually care about from the hundreds of fields that there are. So there's an extract phase where I extract the fields that I care about from just that log event. Then I perform a grouping, which is the aggregation, the dimension that I'm aggregating on, which in this case would be the tweet ID. So I'm grouping on the tweet ID. And then I perform some measurement, which is a count. In this case, I'm summing. So I'm summing across all the favorite events on that grouping dimension, that is the tweet ID. And then I store this aggregate somewhere, which could either be in a relational database, so you can access it, or in a key value data store. It depends on your scale and from your application's use case. And we'll talk about some of the use cases that there are. So to go through an example again, like the event logs could look like, I have some API endpoint, I have some response code of the event that took place on when I hit this API endpoint. There's the client application, like the OS type, whether it was an iPhone versus a web versus Android, etc., that made the actual call. I extract only the fields that I care about. So in my previous event log, as I said, we could have hundreds and hundreds of fields. I extract only the couple of fields that I care about. In my aggregation job. I perform some grouping, which in this case here I'm grouping by the API endpoint. So I'm computing the I'm computing the count of like the different types of response codes based on each API endpoint. So I'm grouping on the API endpoint in this case. So I essentially get a map, and then I collapse my map down. So it gives me the total number of calls that was made to each API endpoint. So I'm performing a summation over here. So here's where I'm performing the measurement. And then I can store the data somewhere. Typically, the two types of places where you would store the data would be either like a key value database, useful if you want to store huge amounts of data that you want to access with low latency, or you might store it in a relational database. Typically, you can store as much data, but it allows you to perform complex queries. You can do like sorts, group bys, limit queries, etc., which you can do in, say, a key value database. So going through a couple of more examples just to drive home the point before we dive into some of the more details about how Tsar is implemented. If you look at the example of API aggregates, which means that multiple calls are made by different client applications to Twitter's API. I want to bucket by each API call, and I want to group on some dimensions, which might include the endpoint that the call was made in, the data center, or the client application ID that was used to make the call to that particular API. I might want to compute, as a person at Twitter, I might want to compute various metrics, which might include the total number of calls made to that API endpoint, the number of unique users that access that particular endpoint, the mean response time for that particular endpoint, and so on. And I might want to write this output out into Vertica because the key space in this case isn't that large. The number of endpoints Twitter has may be hundreds of thousands. It's not in the millions or the billions. So the key space isn't very large, so I can write this data out into Vertica. Also, data like this is typically not going to be surfaced externally outside of Twitter. It's going to be used to build internal facing dashboards. So the latency requirements on it are less. So I can write it out into a relational database like MySQL or Vertica, and it would scale to the needs of an internal dashboard. Even if it loads in a few seconds of time, it's probably fine. Another example, similar, that requires some form of time series aggregation, but that is a little different from the previous one, is that like if I want to open my iPhone app, that is the Twitter app on my iPhone, and next to every single tweet, I want to see the total number of unique users who have seen this tweet. Now this becomes a product-facing feature that is going to be accessed by millions of users across the world. So the needs are very different. The previous one was an internal-only facing feature. Here I have an external-facing product, so the requirements are different. It needs to be much lower latency. It's a much higher key space because I'm aggregating on every single tweet in this case. So the key space is millions, maybe even billions in this case. But the essential core of the problem is the same, where I want to group or bucket by some dimension, which in this case would be the tweet ID. I want to produce some metric, that is, I want to count something, which in this case is the impressions on this tweet ID. And then I want to store the data. Where previously I was able to store the data inside Vertica, here I might want to store the data inside a key value database. Key value store so that you can access the data in low latency. And you can it can scale to the needs of the Twitter app, essentially. And then since it's written out into a key value store, I need some way for the Twitter app to actually obtain this data. So I expose this data via a high SLA query service, which typically in the case of Twitter speaks thrift. And you might potentially want to write like a sample of this data to Vertica to perform like validation or perform internal metrics, like tweets that are sent out by people who have more than 100,000 followers. Like impressions on those tweets, maybe I write that out into Vertica. So just a small subset of data so I can like inspect it, run some queries if I want, do some debugging, some quick debugging. Because it's hard to do that when you write out to a key value database. These two problems slightly different, but are kind of at the core, they're both time series aggregation problems that have different requirements based on their application use case. So what are some of the basic problems that come up when you perform time series aggregation? The biggest one is service interruption. Twitter is a real-time platform. We want to provide real-time analytics to Nike so that if Nike sends out a promoted tweet, within a couple of minutes, they can see how many people are impressing their tweet. So this requires some real-time component to your analytics job. What happens when your real-time component suddenly goes into like a garbage collection issue? It gets too many events in a single like promoted tweet, and so it suffers from data skew and is unable to keep up. Some node goes down, it hits a bad host for whatever reason, and so it loses a few minutes worth of data. It's unacceptable for Twitter to display data to an advertiser and say, hey, like from like 11:55 to 12, we don't have data because our real-time topology went down. We need to be able to build in some fault tolerance so we can surface data even for that period to the advertiser. How do you build in that particular fault tolerance in your analytics system? It requires performing data store coordination. So analytics data could be used for various reasons. You might want to store your data inside a cache so you can retrieve it quickly. You might want to store your data on disk so that you can retrieve data from years back, because very often you want to do year-over-year comparisons on how like you performed during, say, the Super Bowl or during New Year's or so on. You might want to store your data back on HDFS so that a further downstream analytics job can pick up the output of your aggregates and then do some further processing. You might want to store your data inside a relational database. You might want to store it inside a key value store. So there can be many kind of places where you might want to store it, and you would have to define a data model for each one of these. Further, very often, when you first start off working on an analytics job for, say, an application or a use case, you build like some version, like a V1 of your job. You get user feedback, which could either be internal customers or external customers, and then you iterate on this. You change your schema. Your product manager says, hey, like you've been providing impressions on tweets only. Let's now provide impressions on tweets also broken down by client application ID. So you want to evolve your schema. And how do you make your schema and your analytics pipeline in your job be flexible to this kind of schema change so it can evolve very easily? That becomes a challenge. And then lastly, and probably one of the most important things that gets overlooked very easily, is how do you make it easy to perform backfills or restatements? Because as I talked about the example where as you evolve your job into a V2 version, your PM or your like users would ideally like to see that same evolved version of your job for, say, the last 3 months during which V1 was there as well. So how do you go back and like update this historical data that you've already computed? Or say I'm an engineer. Engineers make mistakes. It's human error. Like I made a change to a job that's running in production, and I deployed it with a bug. And so I've been computing some incorrect metrics or incorrect data for, say, a couple of hours. And then I realize this and I fix it. And I deploy the correct version of my job. But it means that for those 2 hours in the middle, I have stored incorrect data in my data store. How do I go back and update this or repair this historical data that I've computed? So making it easy to perform backfills becomes a challenge. It's very, very common for, and I've seen this many times, and we had this problem for the first 6 or 7 months before we actually decided to build Tsar, is that we would have human error, and then it would become a real pain to actually update or update this historical data. So making backfills a first-class citizen was one of the primary goals as we set out to develop Tsar, essentially. And the goal is these are some of the problems that I've outlined, and the goal as building out Tsar was to solve these problems in a general way, so solve them once and for all. So Tsar's main design principles that allow us to solve some of these problems. I'll walk through a few of them. The first one is hybrid computation. So hybrid computation means that every event that comes into Twitter gets processed twice by us. This means that an event, as I said, was say I favorited Sally Ann's tweet. That's an event. That event gets sent into Twitter. It gets processed by some service. That service sends that event to our real-time topologies so that they can pick the event up in real time. That event also gets scribed onto HDFS so it can be picked up by an offline job. So here is where the core of Hummingbird comes in. Where I said the Tsar framework is tied very closely to Hummingbird, is we have an offline job that processes that favorite event, an online job that processes that favorite event. We then have the query service that is extremely smart, and what the query service does is it favors the data from the offline whenever possible, and only for the period that the offline job has not run does it actually query the real-time layers. So let's look at this example. It might help illustrate what I'm talking about. An event comes into Twitter, that's A. It would go into the batch layer as well as the speed layer. So it goes into both layers, gets processed by both of those aggregation pipelines. And then the query service would first query offline, and it says, hey, for this tweet ID and for this hour, do I have a count that has been computed by my offline job? Offline jobs typically run at, say, a cycle of, say, every 4 hours or every 8 hours or a daily job or so on. But I want to give up-to-date counts to the advertiser. So I favor the results by the offline, and only for the period that the offline job has not run up to the current time do I take the data from the real-time component. So what does this mean? This means that offline jobs are typically more stable. They are MapReduce jobs, so they can process much more amount of data. So it gives me the stability of an offline layer while giving me the recency of real time. So now say if my real time layer goes down or goes into GC, I'm confident that in a few hours, whenever my offline job comes along, it will have processed that log event and store that log and would compute the aggregates that are required and actually surface the real number over to advertisers. So it is eventually fault tolerant. The system becomes eventually fault tolerant. That's the key aspect of providing hybrid computation. The second design principle is we separate event production from event aggregation. What I mean by this is events come into Twitter, a favorite event comes into Twitter. As I said, in the example that we talked about where I have multiple log events, I extract the fields I care about, I perform some grouping, then I perform some measurement on the fields that I have grouped on, and then I store the data somewhere. These aspects are common to every single job. The parts that differ from job to job are what dimension should I group on, what are the metrics that I should produce, what granularity should I aggregate on, should it be hourly or daily or minutely, what data store should I store the data in. But those can all be configurable values. So the actual business logic of taking the timestamp of the event, rounding it down to say the hour boundary, or figuring out what the data model is that should store the data inside my key value data store. Those are all handled by the Tsar framework. The Tsar framework, what the user needs to do is specify how he should produce the events. That is, I have a log event that I'm reading from, what are the fields that I care about, and what are the dimensions that I want to produce. The further downstream steps of actually writing the business logic for computing, for providing the groupings, for creating your data model, for spinning up your query service, for spinning up your observability, your alerts, etc., that is all handled by the Tsar framework. The whole point of this, the event production and event aggregation the distinction, is to allow the users to only focus on their business logic, and all the other workflows are handled by the Tsar framework. This point will become a lot clearer once we actually go through an example of a Tsar job, which is coming up in a few slides. The third design principle is a unified data schema. As I said, an analytics pipeline would want to store data, say, on HDFS for further downstream analytics jobs to pick up. It might want to store its data inside a key value data store. In our case, Twitter calls it Manhattan, which is like a custom key value store that we built out. Think of it something like a Cassandra. We might want to store it inside a relational database like Vertica or MySQL, or in a cache. Further, we might want this to be extensible to other schemas. Like today, if we don't support HBase, but if we want to store it inside HBase, we can easily plug in a new sink for HBase, and then every single customer or SAR can then write data out into HBase, and so on. So how do you provide a unified data schema that scales to the needs of billions of events, and that doesn't take up too much space storage, but that doesn't take too much time to query or write into, and that is also flexible to schema change? That becomes a challenge that the SAR framework tries to solve. So typically, data schema coordination is, I have data coming in from either a Kafka spout, which is consumed in real time, or some event logs in HDFS. I produce some aggregates that then get stored inside Vertica or inside Manhattan, for example. And then the fourth one is that we provide an integrated service toolkit. And so what this means is any analytics pipeline at Twitter has to be robust. So you need to have observability and alerting on your real-time jobs. You need to have observability and alerting on your offline jobs, on your query service. You want to have some form of anomaly detection. So if you're computing data and your data that you're computing is corrupt, you want to be aware of it so that you can surface that there's an anomaly to your advertiser. So the data integrity checks, there's alerting and observability. There's ease of there are so many different moving parts to any analytics pipeline. So providing an easy toolkit so that you can easily manage them, you can deploy them, you can make changes to them. That was one of the goals of SAR, to reduce the operational burden and load on the user. So I've spoken a lot about some of the problems of time series aggregation, some of the design principles behind SAR. Let's actually maybe dive into a specific SAR job, and that might help motivate more of this discussion. So the example that I wanted to go through was the example of tweet impressions. We talked about this where, say, if I open my Twitter app and I want to count impressions on every single tweet ID. So here I'm grouping on the tweet ID. I'm producing a count. Since it's a user-facing product, I would want to store it inside a key value database. The challenges here are, we get 500 million tweets in a single day. We get tens of billions of impressions because any tweet is fanned out to all the user's followers who can all impress the tweet. Impress meaning view the tweet. I want to get real-time updates, and I want this whole system to be production-ready and robust. So how do I build such an analytics system? So a minimal SAR project has three components to it. We have a Scala SAR job. So the SAR job is written inside Scala. It's built on top of Hummingbird, which is also in Scala. There's a config file, and there's a thrift IDL where you specify the dimensions that you care about. So there are typically three components, and we'll walk through all of these three components now. So the thrift IDL is where you would specify the dimensions that you care about. In this case, I'm just grouping on the tweet ID, I'm computing impressions on a tweet ID. So the only dimension that I actually care about is the tweet ID. So I define a thrift struct and call it, just have one field inside it. Here is the actual SAR job, and we'll walk through this more. So this is where we'll spend some of our time. So SAR, the parts that are in blue is the custom SAR DSL that we built out, which we believe makes it easy to specify what you want to aggregate on. So the onKeys block is where you specify the dimensions that you wish to group on. In this case, I want to group on the tweet ID. So you would write tweet ID over here. Because tweet ID was part of your thrift struct, we pick it up using Scrooge reflection over here inside the onKeys block. You want to produce some metric, which in this case would be a count. You want to produce a count of number of people who have impressed this tweet ID. Other metrics that you could have here might be a unique computation, a ranking, a standard deviation, a mean. You could have different kinds of metrics that all ship out of the box within the SAR framework. Then you have a sync to block, which is what data store do you want to write your data out into. Since this is a user-facing product, we write our data out into Manhattan. Manhattan meaning a key value database in this case. Or I might want to write my data out into Vertica, in which case I would replace this sync to block with Vertica instead. And then the from producer block is actually what calls out into the Hummingbird API. So this is the actual Hummingbird fragment, which describes the event production logic. So if you walk through this, this is saying, read from the client event source. The client event source is a stream of events that are sent by every single Twitter client, meaning Twitter for iPhone, Twitter for BlackBerry, Twitter for iPad, Twitter for Android. They all send a struct called the client event struct that is sent by clients back into Twitter. So I want to read from these events that are sent by all of the different clients that are coming in real time or in offline via HDFS. Now, every event is getting sent. So favorite events, retweet events, reply events. In my description of my application, I only care about impression events. So I first filter down to impression events by calling as is impression event library or helper function. And then I produce the event, where the event that I'm producing is I only extract the tweet ID. So I'm calling event.tweetID. So the event could have lots of information, like the user that performed the impression event, on whose tweet it was that the impression event was performed, what was the timestamp, what was the data center, so on and so forth. I only care about the tweet ID field, which is the only field that I extract. And then I output a tuple, which is the timestamp that the event occurred, and the fact that this my thrift struct that I'm aggregating on, that I just defined in the previous slide. So this is where I'm producing the event. Notice that in this slide, there is absolutely no aggregation logic being specified. I have not defined how I'm going to serialize this key that I'm producing. I have not defined how I'm going to round this timestamp down to an hourly granularity or a daily granularity or so on. I have not defined how I'm going to produce my count metric. So where is this sum happening? Where is the dot group or dot sum that is happening? None of that has been defined in my Tsar job. That is all completely abstracted away from the end user by the Tsar framework. So the Tsar framework's goal is a user simply specifies these are the dimensions I want to aggregate on. These are the metrics I want to produce. Here is where I want to store the data. And these are the events I want to produce. The logic of performing the aggregation is completely handled by the Tsar framework. The Tsar framework has enough information from this file to extract all the other relevant bits. So the configuration file, which is the last piece of the puzzle, is over here. So walking through it, you can namespace your job so that different people in your team can have like a namespace. You give your job some name, which might be tweets or tweet impressions in this case, the user who's deploying the job, an origin, which is when you want the job to start running from, which might be, say, the 15th of May of 2014, so you have some history. And then in the outputs block is where you specify what granularity you want to aggregate on. So I want to aggregate and write data out into Manhattan at, say, hourly granularity, which is why I specify as sync.Manhattan and width of, like, say, 1 day, or daily granularity in this case. So I'm producing daily aggregates in this case. So that's all the information that the user needs to provide. So in our Tsar job, what are some of the things that we have specified? We specified what is the event schema, which has been specified in Thrift, how we're going to produce the events. Again, I make a distinction between producing events and aggregating events. We specified how to produce events. And we specified various, almost like config options, dimensions to aggregate on, time granularities you want to aggregate on, the sinks you want to write to. What we don't specify is how are you going to represent your aggregated data? How are you going to represent your schema inside MySQL or Manhattan? How are you going to perform the aggregation? How are you going to connect to your underlying services? That information is all handled by Tsar over here. And the beauty of the Tsar framework is it provides you an end-to-end service infrastructure with a single command. We give you a command line tool that you can use. And when you run the command line tool, which is called the Tsar command line tool, you run Tsar deploy to the production environment. It does a whole host of things for you. It will deploy your Hadoop jobs for you, your Scalding jobs for you. It will deploy and launch your Storm jobs for you. It will launch your Thrift query service for you. If you're storing data inside Vertica or MySQL, it can also launch loader processes so it can pick up the aggregated data stored by your offline job on HDFS and store it inside Vertica. We use Aurora and Mesos as our schedulers for our offline jobs, which require some configs to be generated. It infers those and auto-generates those configs. It generates alerts for your batch jobs, your query service job, for your online jobs. It generates observability for all of the different components of your pipeline. If you've integrated with the anomaly detection framework of our thing, it will automatically generate anomaly detection alerts for you. So say you're computing impressions on tweets, and the total impressions on a particular day is, say, like some number, say 100x. And on a particular day, the total impressions ends up being 50x. You're like, hey, where something is off. Maybe the iOS developer made a mistake and stopped logging impressions on the iOS client. So you get alerted to these kind of anomalies. If you're storing data inside Vertica or MySQL, some table needs to be created, some view needs to be created over those tables, some projections need to be created. It will automatically figure out that I need to go into Vertica, create a table. What is the schema of the table can be defined by the DSL. So you know that you're aggregating on the tweet ID and I'm producing count. So you know that you just have to have two fields, in two columns in your table, which is the tweet ID and the count. and maybe the day granularity, so you have a day timestamp as well. So all of this information and all of these various steps are performed by the Tsar tool in this case. So Tsar builds on top of Hummingbird and makes it very easy for the user to build upon the frame, to like do things essentially, like to just focus on the business logic and get an entire analytics pipeline up and running very easily. So a bird's eye view of the Tsar pipeline looks something like this, where we have log data on HDFS, typically which that reaches there by Scribe. We have real-time streams coming in, which could either be, say, Kafka or Kestrel. The log data gets aggregated on by scalding, that is bad jobs. The real-time data or Kafka streams get aggregated by, say, storm jobs. This layer is like what we call the Hummingbird layer. So a Hummingbird job translates into scalding and storm. Then if you want to write data out into Vertica MySQL, there's no like real-time component. We don't have a real-time job hammering into Vertica, but you can write offline data there to do ad hoc investigations that can then be used for data exploration or for internal dashboards. If you want a user-facing product, you could write your data out into a key-value data store. So your offline and online job would go into Manhattan. Using the Hummingbird Storehouse batch libraries, there's a thrift query service that queries this data and then can be queried by a public-facing dashboard to provide like a time series to the advertiser. So that's roughly what a bird's eye view of the pipeline looks like. So now say like, what is the beauty of Tsar framework is, okay, now I've built my analytics pipeline and I'm very happy and like the developer's gone home. But now product managers, which are the bane of my existence, suddenly decide to come and is like, hey, like I want to do something different. So the product manager is like, okay, I broke down impressions by tweet ID. Now let's break down impressions by tweet ID and also client application ID, because that's more useful information that like I want to surface or gain an understanding into. In a typical case, you would have to go update your offline job, update your online job, update your query service, update your schema inside Vertica to add a client application ID column, do a bunch of things, update your observability, your alerts, etc., etc. In Tsar, sorry, I skipped ahead. In Tsar, you add one line into your onKeys block saying I want to aggregate on tweet ID and client application ID. And then in your produce events place, you extract the client application ID from the raw event. And you run Tsar deploy, and it will automatically do everything for you. So it allows you very easy schema evolution in this case. What about, okay, so my product manager says, okay, great, you've done this work for me, but your old version of your job has been running for 3 months. I also want this broken down by client application for the last 3 months. Okay, I run a command that says Tsar backfill and I pass it a start time and an end time, and it automatically spins up a backfill job that runs in parallel to the production job. So the production job continues to run onward, and a backfill job runs in parallel to the production job and comes in and generates my new data for me. This can be useful for repairing historical data as engineers make mistakes, as we talked about as well. Okay, now say I've been aggregating on daily aggregates. I now want to produce an all-time aggregate. So how many impressions has this tweet gotten in all time? Or I want to produce hourly aggregates. If you remember, my configuration file had an output block which said the sync and the granularity. I now add a single line to my granularity which says width equals all time. And I again run the Tsar deploy tool, and it would begin to generate all time aggregates for me as well going forward. Say I've been computing total counts. Now I want to actually compute number of unique users. So for example, in the old example, say I have viewed a tweet at 11 a.m. and then I view it again at 4 p.m. That would count as a count of 2. It's raw counts. Actually, say I want to compute like a reach, like the reach in frequency, like meaning how many unique users have seen my tweet. So I can add a column that says unique user IDs, and I deploy it, and this will now begin, and I extract the user ID field in there. So now I begin to get number of unique users who have seen my tweet. Anyone see any problem with this? So say like I have number of unique users who saw my tweet on day 1 is say 100. Number of unique users who saw my tweet on day 2 is say 50. Number of unique users who saw my tweet on day 3 is say 75. So, and I get a query to the Tsar query service that says, give me the number of unique users who saw my tweet between day 1 and day 3. Anyone know how I would do this, or any problem with doing this? Sure.
You have to, for each unique user, where do you put your one view? The time they initially viewed it, the last time they viewed it, and if you only look at a window, which one does it fall in?
Okay. How would you do that though? Okay. Anyone want to try?
There are approximate counting mechanisms.
Yep, exactly. So precisely. Someone said that there are approximate counting mechanisms. So the problem is that if I have 3 unique counts, I can't add the 3 to get another unique count. So uniques can be backed by something called a hyperlog log, which is a data structure that can provide approximate unique counts in a very efficient manner. So I would store a hyperlog log in my data store that represents the unique count for day one. Similarly, a hyperlog log that represents the unique count for day two, a hyperlog log that represents the unique count for day three. So when I get a query over the 3 days, I extract the 3 hyperlog logs, I merge them together to form one big fat hyperlog log, and then I derive this hyperlog log to actually give a unique count. So this is all done at query time. Now, I'm an application developer. I don't really want to go and implement hyperlog logs. I don't want to do this kind of optimizations. So the Tsar framework automatically figures out that, hey, I want to do unique computation. Okay, let's go and store hyperlog logs. Similarly, if I want to do percentiles, it goes and stores Q-trees, which is another data structure that performs and does percentiles. Say I want to compute top metrics like rankings. It goes and stores a sketch map instead. So it has multiple derived metrics that are backed by probabilistic data structures that do approximate counting. And these probabilistic data structures are even smarter. So say for unique counts, say like I have a tweet that only receives 2 impressions. Since it's probabilistic, I don't want to report like 3 or 4 in this case. I actually want to report 2. So the unique counts are exact up to a certain cardinality. So say I can set a cardinality saying up to say 1024, I will maintain an exact set. And only when the cardinality of my set exceeds this value will I convert it into a hyperlog log data structure. So it's approximate but exact up to a certain threshold. And only when the threshold is like exceeds some amount after which you can begin to be a little bit probabilistic. And these are all baked into the Tsar framework and the libraries that it uses, in this case AggregatoR. So it makes it easy for users to do this. And then say I've been persisting data to Manhattan, I want to persist data to MySQL as well. I add a new line to my Tsar job that says, okay, sync to MySQL, and then I run Tsar deploy again and now begin to have aggregates inside MySQL. So a typical Tsar workflow is I create a job, I deploy it. If I want to modify my job, I can modify it, and then I deploy it again. And if I want, I can optionally run a backfill as well in this case. So I have actually a few slides on Tsar optimizations, but the conference organizers tell me that I'm coming out of time. So I know that the slides have been sent to the conference organizers, and they're available online on SlideShare if you Google my name, a lot of these optimizations and everything. So I'll skip over these. I'm happy to chat with anyone offline about them. So there are a bunch of optimizations that we've done to make Tsar like more efficient and scale. But in conclusion, I wanted to say that like the kind of 3 problems that Tsar tries to solve is the computational management aspect of things, which is I specify aggregation dimensions, metrics, and time granularities. Tsar goes and automatically figures out how I want to do uniques, how I want to do rankings, how I want to do percentiles, how I'm going to like round data down to hourly granularities or daily granularities, how am I going to take into account different time zones of advertisers. It allows for data set management. So how do you store data in different schemas? How do you evolve these data schemas? How do you coordinate data migration, backfills, recovery? And then there's the service management aspect of it, or operational load. So Tsar tries to reduce the operational load on people, on users in general. There are lots of moving parts. How do you make it easy to manage these things? How do you make it easy to observe these things, provide alerts on these things, data regression checks on various things? Tsar gives you all of the above, essentially. So there's one key takeaway from my presentation. It's the entire end-to-end management of the data pipeline is like Tsar's key feature. The user only concentrates on the business logic. Thank you. If you have any questions, you can reach out to me on Twitter. My handle is Anirudh Todi, or you can email me, ani@twitter.com. We're also hiring. So I recently became a manager of the revenue analytics team. We're directly using the Tsar framework. So if you're interested in learning more, reach out to me after the presentation. But thank you.
Thank you. And we have time for a question or two.
Hello. So you talked a lot about schemas being utilized in Tsar.
Sure.
I was wondering about kind of getting the schemas into Tsar. If you go back to that slide in the from producer event, it looked like there was a method is impression event, and you extract values from the schema. I just wonder a little bit about what that storage and kind of validation, or how that information kind of flows through, so that you know to say, hey, pull out the event.tweet ID, or know that it is an impression event.
Sorry, so
I guess my question is, what do the schemas look like before Tsar? How is that handled?
Oh, sure. I mean, the schema, like the events that come into Tsar look something like, so the question was, what do the schema of events look like before they come into Tsar? So a typical event that comes into Tsar would be something that's, say, thrift encoded. Like typically thrift is what we use at Twitter. So like a client event, as we talked about, might be, like in this case, it's not exactly a client event, but think of it like is some thrift event, which is say a flat structure, or it doesn't have to be flat, it could be nested, is what are the different fields? In this case, like the API endpoint, the response code, the client. In the case of client event, the different fields you might have might be the user that created the event, the tweet on which the event was created, what time the event was created, which data center the event was created in, whose tweet was being favorited, and so on. So those are the kind of events that come into SAR. The SAR job would now like pull out the fields that it cares about. So, sorry. Trying to jump around here. So in the SAR job, like in the second to last line, we pull out the fields that I care about. So in this case, I pull out just the tweet ID fields by calling event.tweetID. And this is the thing that I send down. Now, the SAR framework then takes over and realizes that I'm aggregating on tweet ID and I'm producing counts. So I should like do a .group on tweet ID and then do like a .sum or something along those lines. And then like it then serializes it using like a codec and stores it in binary format inside a data store that can then be deserialized at read time. And there are various optimizations in the SAR optimization slides that I had to skip over on how we store it efficiently so that it can be stored efficiently and queried efficiently as well.
Maybe one more quick question.
Hi, great talk there, by the way. So I have a question about open sourcing.
Sure.
Hummingbird is actually dependent on the underline of Scalding and Storm.
Yep.
You actually released a paper about Aaron, which is going to be 3 times faster. So you're actually using Storm or you're using Aaron on production? And when are you actually, what's the plan about open sourcing Tsar and Aaron?
Sure. So Storm is, I believe it's open source. We have been developing a new compute framework at Twitter in general, which I believe is not open source, but there are talks of like open sourcing that. SAR is something that we've talked about open sourcing, though there aren't any plans to do so at the moment. The two main reasons for doing that is one, it's a lot harder to open source a framework than it is to open source a library. The amount of work required to do so is much, much greater. And the second reason is just that SAR is very, very closely tied to a large part of Twitter's infrastructure. So, like for example, one of the big goals that like SAR provides is how do you reduce the operational workload on the user? Because it makes it easy to plug into observability systems or alerting systems because the SAR2 like integrates with them already. Like it gives you that to free for any application developer at Twitter. But in open source, that's not exactly going to work. So the parts of SAR that are useful in some ways to open source would be say the SAR DSL and how it like fans out into the different like probabilistic data structures that are in the background. That's something that we've considered. It's something that just hasn't been done or prioritized as yet because it's a lot harder. It's all very tightly coupled with Twitter's infrastructure at the moment.
Thank you, Ani.
Okay, thank you.